Good evening, all. Everybody hearing me? Can just everybody send like a message? Yes, yes, yes. So I know that everybody's hearing me. Most people are using Skype web app, right? So what I'll be asking you to do is to keep your, you can speak, anybody can speak at any time. I don't control that. It's like in a class, but respectfully, keep your mics muted. If you need to ask a question, just unmute, ask your question. Everybody hears a question, I give the answer, or if I have an answer. Clear? See, some people are not here right now. That's Demar, Jordan. They are logged in, but they're apparently not looking at the screen. Anyway, yeah, I've started to record, so please remember to remind me each time to record. All right. Okay, before we go into the lecture, you can't see anything, Jordan? I realize you can't see anything. That's what this thing tells me. So I think there's some controls that you need to. Can anybody tell him what to do? I would have to play.
Yeah, you can see it now.
You can see it now, Jordan?
Yeah.
Okay. Alright, you can mute back yourself, Richard. Thank you. Alright. Demar, you're not it says you're not watching the presentation. Can you see what's going on? Demar is not answering. Anyway, we have 12 persons. I think that's enough to start the class. This looks good. I'm in my farm somewhere in the bush in Clarendon. And we're all good to go. Alright, I'm just going to go to where we left off. Okay, so I encourage everybody every now and then unmute, say something, just so I know that you're listening, and I know that I'm kind of catching it. You understand? I don't always have to look at the messenger to see that you're listening.
Yeah, man.
Alright, good. Thank you, Franklin. So back to where we were. Is everybody still seeing the presentation? You should see a full screen. Please confirm that that's what you're seeing. It should be on the main page. Good. Alright, I'll leave it as is. Alright, so we had stopped last week. I'm not going to spend too much more time on linear systems. Much of what is left to be done, I'm going to be actually requiring the class to do their own research to understand these elements. But last week we established a few things. The basis of linear algebra, or what is a linear system? One in which dependent and independent variables or quantities have a linear relationship. That means, for example, whatever amount you increase one variable by, the dependent one increases by a proportional amount all the time. So proportionality, let's say it is 3. It means if I increase one thing by 1, the other one always increases by 3. That's what proportionality means. Yeah, that's what linear relationship means. Not proportionality, but a linear relationship. It's proportional if they both start at 0, but if they don't both start at 0, that means if there's a non-zero intercept, we just call it linear. Okay. Now we had discussed that you can have several different types of problems or several different possible solutions. It depends on the number of independent equations, which is called the rank, and the number of variables, which we normally just call m, or you could call it the number of columns in the A matrix. You should also recall that the A matrix is really called the coefficient matrix. So if you have 10 coefficients, it means 10 independent variables, or 10 variables that make up your system. Alright? Any questions so far? Yes, I'm recording, Judah. Demar says he's not seeing. I realized Demar wasn't seeing from the beginning. Could somebody tell Demar, Judah, could you tell Demar what to do? Because you weren't seeing. Oh, you're not seeing either. Okay, could somebody tell Demar or Judah what to do? Because I realized both Jordan and Demar are not seeing. Anybody know what to do so you can see? How do you cause somebody to watch a presentation? Odeon, that's OD, I'm guessing. Is OD Odeon? Somebody just named OD just came in. Is Odion? Hello? Yes.
It's Odion.
Okay, good. Thanks, Odion, are you seeing the presentation? It's my
Just see
what do you see?
blank, dark screen. So rejoin.
So click on rejoin for me now. For some reason it's telling me that you are not seeing the presentation. I'm not sure why.
No, I'm not seeing it. Some other participants, group members.
Yeah, I see.
I click on the grad engineering UTech.
And it's, the thing is, I don't know what you're seeing. I couldn't tell you what to click on. Alright, hold on. Just give me a minute, alright? I'm going to do a quick check. I'm going to mute my mic briefly, folks. Just checking something. You just came out of presenter to attendee audio. Whatever you did, just undo yourself. Make yourself a presenter also. Yes. Yeah, Jordan, I realize. Yes, hello.
That's on you.
Who is this?
Ennis?
Ennis. Yeah, man, some folks are having a little trouble, so I'm just giving. For some reason, three people can't see the presentation. You're seeing it, right? Should be on LUD. It's the LU decomposition, right?
Yeah.
Yeah. Okay. Try. But them are Jordan and Odian are not seeing it.
Can you have more than 12 participants?
Yeah, man. It was just at 13 a while ago. Were you told that you can't have so many?
Yes, it's just Jordan. You can't see it now.
Jordan and Odian can see me now. No, Odian can see me now. Odian, what did you do? Odian, unmute and tell me what you did.
Still loading.
Yeah, but now you can see, right?
No, I see a loading icon. So it seems that, yeah, I see it now.
But you didn't do anything for it to load.
No, what happened? I had to rejoin.
Oh, you had to rejoin.
Right.
And
But
you
I've
did.
seen it now.
Yeah, but when you rejoined, you didn't do anything different. You did exactly the same thing you did before.
No.
What different did you do when you rejoined?
Actually, when I rejoined, I pressed the same, just the rejoin button, because the first time, when I pressed the rejoin, it was loading and then it kicked me out of the software. So I had to reinstall and then press rejoin and then it connects. So,
Okay. Alright. Jordan, you want to try? Okay, so I think Jordan is trying. Demar, I know you still are hearing me, but you still cannot see the screen. I need you to try again. Everybody else is seeing though. Demar is not even hearing me. Yes, Kevoy, what? You can just unmute Kevoy and talk. Oh, you're just saying yes. Alright. Alright. Probably Demar is not at the computer because since I've been here, been saying stuff. Oh yeah, there Demar did say something. Oh yeah, he says he's not seeing. Demar, could you come out and try again, please? Okay. So Jordan is back. Jordan, you're seeing now. I see Jordan is in and now it's working. So Jordan, alright, Odian, you can mute yours. Shanara, mute yours also. And I'm going to ask Jordan to tell us, unmute Jordan and tell Demar what you did. Talk, man, just unmute and talk. Okay. All you did is log out and log in again. Oh, you don't have a mic. Alright, got it. Demar, are you there? Okay, I guess I'll have to continue without Demar's input. Alright, so let's keep going. So, quick review. So we have different possibilities when you have a linear problem. The rank is the number of independent equations. It's not the number of equations. So your little mantra that you used to learn back in undergrad, or even in undergrad, that said number of equations must be equal to number of unknowns. That's not quite true. It is number of equations must be number of independent equations, linearly independent equations, must be equal to the number of unknowns. That is the truth. Okay? The number of equations can be equal, but if more than one equation is added together, you can get additional equations, but they are not independent of each other. So that's the most important thing. So you have several possibilities. First possibility is, can you get a solution? Or the first question is, can you get a solution? You can have several solutions if the rank is less than the number of unknowns. That means you don't have enough equations to solve the problem, independent equations to solve the problem. If the rank is equal to the number of unknowns, then you can have a unique solution. And if the rank is more than the number of unknowns, that means you have more equations than unknowns. You are over constrained. You have over constrained your problem. You don't have a solution to that problem. Alright? So if at any time your rank is more than the number of unknowns, then something is wrong with how you model your system. Now, if the rank is equal to the number of unknowns, there's a second consideration. It is whether or not you can trust the solution that you have. And that has to do with conditioning. You can have a problem that's well conditioned. What does well conditioned mean? That means if you change the answer slightly, change the inputs slightly, for example the coefficients, or if you change the non-homogeneous terms, that just means the constants that don't have a coefficient. Usually the way the equations are expressed is that you have the linear terms to the left. That means the coefficient times the variable plus coefficient times the variable plus coefficient times the variable. That's put on the left side of the equation, and then you have the constant on the right. So if you change any of the coefficients or the constant by just a small amount, your answer should change by about the same small amount. A well-conditioned problem is one in which when you change one thing slightly, it changes your solution about slightly. Now your solution can never change to the exact same degree. For example, if I change my input by 1%, my solutions should vary by 1% at the least. It may change by 2%, but it can't change by less than 1%. Alright? That's just how it goes. Alright? So, but you can have a case where you may change your input by just 1%, just a little slight change. For example, you have a number 22 and you change it to 21.8. Right? That's a 1% change. This is some constant or coefficient in your system is 22, and you change it by just 1%. And when you change it by 1%, one of your answers changes from 50 to 70. Right? 50 to 70 is like a 40% change. That implies what we call an ill-conditioned problem. How do you determine if something is conditioned or ill-conditioned? You have to calculate something called the condition. That's all, the condition. And what is the condition? It is the norm of the coefficient matrix times the norm of the inverse of the coefficient matrix. Alright? And if the condition is, let's say, much larger than 1, much larger always means at least 10 or up, 10 or 100, then it's ill-conditioned. 10 is not good, but you can live with it. 100 is bad. 1000 is atrocious. Right? Anything under 10 is quite satisfactory. Alright? So that's what it's about. I started to discuss LU decomposition. What is LU decomposition? It's a procedure in which you start doing the problem by breaking up A into two vectors, and A is equal to L times U. And then when you do that, you actually have gone through some of the calculations already, so that you can know solve the system. So here we have a case in which AX equal B. I change it to LUX equal B. Alright, now the first step is to first solve for L. What is D? D is equal to, please note this, let me get some notes, make some markings on this. Annotations, hold on. Okay, I'm not quite sure how to make the annotations, so you have to give me a little time to work this part out. I don't think I'll do it this presentation. Probably I'll figure it out for the next presentation, so bear with me. Alright? Everybody was hearing me alright? Just type a little yes. Let me know that you're hearing me. Good, good, good. And I'm not too broken up, right? You're kind of hearing me okay. Alright, good. Glad to know. So, when you do a LU decomposition, here is our vector. 1 minute, please. Okay, here's our vector. Here's our system. LUX. LU is the same thing as A. All right. So what instead we do is we're going to make up a new set of independent variables called D. What is D? So we're going to say we're going to solve for LD equal B. Remember, you found what L is already, and you know what B is. So the independent, or the unknown, sorry, is D. So after you solve for D, remember you called UXD. So after you found D, then you're going to solve for X. That's the second step. Alright? All we're saying is these two operations, after you did the LU decomposition, these two operations go quicker. Why are they quicker? You may recall when we were, let me go back quick to slide, when we were doing LU decomposition. Hold on. Not LU decomposition, we were doing Gaussian elimination. I just want to show you something. Showing you something here. Everybody should recall. Here we go. So when we were doing boy. Okay, here we go. We went through all of these stages. All right. add is, note what this is. This is a upper triangular matrix. See it? It has the upper part is non-zero and the lower part has to be zeros. Okay? Now, if you recall, this actually is most of the way to the solution, because you realize you in this case x3 equal 2. Once you have, yes, insert it, you're not seeing it change for you. If anybody wants to, what do you see now, insert?
I'm seeing slide 16 of 29.
Wow.
Decomposition.
Anybody else seeing the Gaussian elimination slide?
No, I see linear relation.
Yeah, what slide is seen on? Oh, wow.
I was seeing more like it.
I'm seeing slide 1. All right. I think that's the problem. Don't worry, I'm going to work on this. Alright, I think I got it worked out. Hold on. Everybody's seeing Gaussian elimination now, right? Okay. So what I was saying is, here, note, you should all recognize that this is a upper triangular matrix. This is like the U. Everybody see it to the right?
Yeah.
Yep. So when you break down your A into U and L, you actually have gone quite a way in solving your problem. Ainsworth still not seeing it. What do you now see, Ainsworth? What slide are you seeing?
I'm seeing the same slide, slide 16 of 29.
Wow.
Decomposition extended to inverse method.
Wow.
Nothing changes for me.
Alright. What are you seeing, Jordan? What are you seeing, boy? Okay, so you're seeing slide 9, which is where I am. So it seems as if your Skype do a little thing where whatever time they take to upload is when they upload.
Yeah, I see slide 9 now. Feel like it has some delay or something.
Who is saying that?
Jordan is saying that.
Oh, I thought Jordan said he didn't have a mic.
Yeah, but I plug it in my phone. I switch it over to my phone, so I have a mic now.
Okay, cool. So Paul just starts in 9. So I realize I'm going to have to speak a little slowly.
I'm going to leave and rejoin and see if that works.
Ainsworth? Alright.
Yeah.
Everybody is seeing 9 now? I think by now everybody should be seeing 9. Alright, cool. So what I was saying is, whenever the original Gaussian elimination procedure actually broke down your A into a triangular matrix. Here's a triangular matrix. Everybody, it's on the right, lower right. Okay? And okay, insert is good now, he says. Yeah, so the lower triangular matrix is there on the right. So I'm going to click through. Please tell me if it's going through when I click. Does everybody see this is Gaussian GJE? Everybody sees that?
Yes, sir.
Well, Kevin, you don't count. I think you have a high bandwidth place. Alright, good.
Yeah, I see. It was good. I see.
Everybody see solution scenarios now?
Yes, we're good to go.
Alright.
I'm good to go. I'm good.
Good, alright. Everybody seeing rank now?
Yes.
Alright.
Yes.
My voice is echoing. Everybody's voice is echoing. So everybody mute now. Thank you very much. Jordan mute. Thank you. Okay, good. Jordan, you're actually logged in on 2 things. I see. All right.
Yeah, I'm using my phone for the mic and the
okay.
whatever and the computer.
Okay, got it. So what I'm saying is, when you do a LU decomposition, you have partway done broken up your analysis. You can mute Paul, please. Paul? Hello, thank you. Right, so when you do a LU decomposition, you actually have partway gone through the process of solving the problem. So now the remaining part is all that's left. Now, if you were only solving one problem, this really doesn't make your analysis any easier. This only helps your analysis if you have to repeat the procedure, but every time B changes. A never changes, but B changes many times, then you can use LU decomposition. Alright? You can also do something called the inversion method. Inversion method simply says you calculate the inverse. It's almost like doing a LU decomposition. Alright? You calculate the inverse of A, and then so whenever you have a different B, you just say A under B, and that gives you your X. A under B, that gives you your X. Every time you change B, you say, when I say A under B, I hope you understand I mean the inverse of A times B. Alright? We talked about the operation called under, which has always really been an operation, but you've never used it because you've always lived in the scalar world. But in the vector world or the matrix world, it depends on the order of how you do your multiplication, right? Alright. So the point is this: if you have the same A but a different B, or you have several different B's, you use LU decomposition to streamline your process so that you don't have to do the whole procedure of the solution every time. You just calculate the inverse once, or calculate the L and U once, and then after that you just do the last part of your procedure. Alright. Okay, and everybody, you should see your assignment. You have until next week Sunday to hand it in. It's on the website. Okay, now what I'm going to this last part that I'm discussing on linear systems is really going to be sort of a research. I'm going to be doing some discussions on the website through the discussion forum. So what happens is sometimes you have different types of A matrices. Alright? When you have different types of A matrices, sometimes you don't really have to do the full blown inversion or LU decomposition. You can do other types, more simpler procedures to get to your answer. So for example, if you have something called the tridiagonal matrix. What a tridiagonal matrix? Tridiagonal matrix is one in which the diagonal elements, that's A11, A22, A33 and so on, are all 0, and the diagonal just above it and the diagonal just below it are all non-zero. Okay, those are the non-zeros. Every other element is a 0. That's called a tridiagonal matrix. It's common in transport problems. Transport problems are problems that have to do with especially transport problems are like in diffusion problems or problems involving heat or mass or things like that. We call it transport problems. Alright, so I will just be asking you to just do some reading, discussion amongst yourself as to different scenarios where the Thomas algorithm is applicable, and to ensure or check if MATLAB has a function that handles these special cases. Alright, remember MATLAB is specially designed for any type of matrix based problem. So you have the Thomas algorithm for tridiagonals. You have another type of matrix called the symmetric matrix. What's a symmetric matrix? Symmetric matrix is one in which you have there's a slight error in this one, so please note the error. But here's what a symmetric matrix is. Every non-diagonal element, for example, the element A52. What is A52? 5 means row number 5 and column number 2. A52, right? Let's say A52 is 22, a value. Okay, 22. A52. If A52 is 22, then A25 is also 22. That's called a symmetric matrix. That means the value of an element and the value of every element. I don't want to say the non-diagonal, because even the diagonal it works. The value of every element is equal to the value of the swapped the element where the row and column is swapped. Alright, so a xy or a nm is equal to a mn, just a switch. In such a case, there is a procedure called the Kolsky decomposition. Again, it still comes back from the LU decomposition, which is a general form. Please investigate if MATLAB has that functionality in it already, and investigate how to use it. Alright? Remember that you guys will have to develop your own codes or your own software toward the end of the class, toward the end of the module. So get used to these possible simplifications. Alright? Because if you don't apply the simplifications, it's going to make your computation very weighty. Alright. Now I'm going to go into a new topic, but it's kind of still the same topic. Alright. There is another way to solve a linear system. It's called iteration. It's called iteration. Let me see if I can explain what iteration is. In iteration, you have to guess your answers. That means you have to guess what is x1, x2, x3, and so on. You make an initial guess. Your guess is going to be, of course, educated guess. It's not really a guess, it's an approximation. You know, based on some information that you may have, you have an approximation. Oh, can you use mouse while you're explaining? I will try. Are you seeing my mouse? Are you seeing where my mouse is right now? I'm wondering. You're not seeing where. Okay, let me see if I can find out how to annotate. Give me a minute, please. Okay, here we go. Are you seeing something now? Please tell me if you're seeing where I'm pointing.
Oh, I see a mouse catch up in the corner.
You see a mouse catch up in the corner?
Oh, no, I'm my mouse. Sorry.
Oh, Judah. Oh, good. There we go. So, can everybody see this now? Nobody sees this? Whoa.
Yes.
Bedard says he sees, John Paul says he sees, Franklin says he sees. Okay, good.
Yeah, I see it.
Yeah, man, it's a green flash, that's correct. So here we have, I'm not flashing it now, you should actually be seeing a dot moving. Is everybody seeing a dot moving around?
Yes, sir.
Alright, good, thank you. So what we have here was the original expression. I want everybody to take out a piece of paper so I can do some exercising. Everybody, take out a piece of paper, please. I want to ask you to write a 3 by 3, a 3 vector, a generic 3 equation system. That means A11 x1 plus A12 x2 plus A13 x3 equal B1. Then under that you write the next equation, A21 x1 plus A22 x2 plus A23 x3 equal B2. And then you write your third equation, A31 x1 plus A32 x2 plus A33 x3 equal B3. Everybody heard what I just said? Jordan, please, man, mute yourself. Welcome, Richard. You're late, but welcome. Which one of the Richards has come in? Oh, hi, Arthur. Jordan, please mute. Hello, Brandis. Just seeing you now.
Hello, sir.
You can mute yourself now, Brandis. Thank you.
Alright.
The mute is... Yeah, there you go. Jordan, please mute. How much time must you mute, man? Oh, is your thing there? Is the thing that's not muted the one that doesn't have a mic? Okay. Okay. So Jan is asking me to repeat the equations. So what I said is you're going to write the the generic three equation system. All right, the generic 3. I'm going to type it. Let's do it that way. Everybody, please note it's going to be in the. I'm going to type the first one. A11 x1 plus A12 x2 plus A13 x3 equal B1. Why see that? And then you have to repeat that now for, and then you repeat that for the other two. Repeat that for the other two equations. So that's just one of the three equations. Could somebody type the other two? Okay, somebody, whoever, anybody, please type the second equation for me. Good, thank you. Ainsworth, let's do the third one then. You're going to do the second one. Ainsworth, let's do the third one.
Not seeing the equations.
You're not seeing the equations in the conversation section?
No, wait just a minute. Just a minute. I think I'm just need to click on the conversation icon to the left of the screen.
Yeah. It's a lower left, right? Lower left, there's
Yes.
also.
Oh, yeah.
Alright,
See there.
cool. Thank you, Ainsworth. 313233. Good. So what I want you to do now is, for the first equation, you're going to solve the first equation for x1. Could I ask somebody else, not Odian, and oh yes, Ainsworth, you did make a slight error there. Thank you for correcting that. Not Ainsworth and not Shanna Roy. Could someone else now solve the first equation for x1? Write it like you would write it in MATLAB, you know, or in Excel, you know, since you can't put the divide sign under everything, you have to imagine that that was your situation, right? So I think Richard is a Cargill who is also trying to solve for it. Good. So Richard says B1 minus A12 x2 minus A13 x3. Yes. Good. It's quite good. 1 second, please. Just give me a minute, please, folks. When I can't talk to myself, just give me a minute here. I have to go check on something. Alright, good, I'm back. So or should I? So yeah, everybody is correct. You do realize there's an error on my slides, right? Just didn't get to fix it. There should be minuses before the A1s and A1, the AXs. Everybody see that? See those errors? Good. So what you just wrote is the solution for x1, assuming that you have x2 and x3. So that means you would have had to guess a value for x2 and x3 to come up with a solution for x1. Okay? Usually what we do is we guess all of them. We guess x1, x2, x3. So could somebody write the solution for x3? What is x3?
For equation 1?
No, for you're going to solve for. Oh, you're asking for equation 1. No, you're going to use equation 3. Use equation 3. Alright, Franklin, correct. Right, let me check. Make sure it's correct. B3. Yup. Good. Okay, boy, correct. So that's x3. So you only could have gotten a value for x3 if you had a guess of what x1 and x2 are. Remember, those are unknowns though. X1 and x2. So you'd have had to have an assumption of what they are. Alright? The general meaning of iteration is to use an initial guess. So you'd have guessed x1, x2 and x3, and then from x1, x2 and x3 you solve for x1, x2 and x3 using this equation. Am I clear? So we call that now this procedure is called Jacobi iteration. Okay, Shanora wants to repeat. Let's say it again. Iteration, we're going to go into that topic actually in a couple of minutes. Iteration means to start with a guess and to improve that guess through a sequence of calculations. Alright, so what we did is we guessed x1, x2 and x3. It's not the solution, it's a guess of the solution, and we're going to use that guess to check how close the guess is. Alright, and when we do that, we come up with an improved, hopefully, x1, x2 and x3, and so on. Understand? We call that iteration. The next topic is actually iteration, so that's why I'm kind of discussing it now. That's the next unit. So this is a segue between linear systems and iteration. All right, this topic. Now, this type of iteration is called Jacobi. What Jacobi does is, Shannon, do you understand? He asked me to repeat, and I've repeated, but I'm not sure if you have to confirm. Yes, boss. All right. Cool. So this type of iteration is called Jacobi. What is Jacobi? That you use your initial guess to come up with your next set of guesses. That means you update x1, your guess for x1, x2, and x3. Your second guess of x1, x2, and x3, and so on, are based on your first guess of x1, x2, and x3. We call that Jacobi iteration. But you can slightly improve it. And the slight improvement is called Gauss-Seidel. I hope everybody saw that the screen changed. It's a very subtle change. Let me go back to the Jacobi screen. Everybody see Jacobi screen, slide 20. And I'm going to now go to the Gauss-Seidel screen. Ready? Gauss-Seidel. Boom. What the Gauss-Seidel does is, when you calculate x1 using the second guess of x1 using the first guess of x2, x3, x4, and so on. By the way, I hope you see the error again. Sorry. Look at the first equation. It really should be x1 second guess, that's I plus 1, is equal to b1 A12x2 first guess of x2 plus A13x3 first guess of x3. Let me click so you see where I'm talking. So this should be A13x3. I is whatever guess you are, so I'm right now at the first guess, okay, and so on. I hope everybody's clear on that. So here we're using all first guesses to calculate the second guess. That's how you calculate x1. Now when you go to x2, since you have already updated x1, you're going to use the updated x1 when calculating x2. But you don't have an updated x3 as yet, so you use still the first guess of x3 and so on. When you get to x3, you would have used the updated x1 and the updated x2 to calculate the second guess for x3. Okay, so what Gauss-Seidel does is, as soon as you do one iterative calculation, you always immediately use that updated value in your next calculation. You don't wait until you go through the full set of equations, but as soon as you do one equation, you will use the updated value that you get from that one equation. Alright? Paul, question? Remember, you can unmute to ask the question too, you know. I honestly, when you come from the techie world, everything was message. So, and everything else remains the same for the other iteration. That's what Paul says. So all I'm saying, Paul, is when I've calculated x1, when I'm going to the x2 calculation, I use the updated version of updated value of x1 to do my x2. I still have only my old value of x3 and x4. When I get to x3, I use my updated value of x1 and 2, but I still have the old value of x4, x5, and so on. Let's say I go to x4, I'll use the updated value of x1, 2, 3, and the old value of 5, 6, 7, and so on. Alright? Everybody clear? Cool. That's called Gauss-Seidel. Alright? Now, Gauss-Seidel and Gauss-Jordan are useful for what's called okay, there's a little problem with these iterative procedures. It is that we learn, you learn it in the next topic, that iteration sometimes veers away from the answer. So you actually are plugging in something, and when you plug it in, you get a worse answer than the original guess. When your answer goes, when your guesses, the guesses each iteration, you come up with an upgrade of your guess. When each subsequent guess gets closer to the final answer, we call that convergence. Alright? And when a guess goes away from the correct answer, we call that divergence. I hope everybody is clear on that. Divergence and convergence. Now, between Jacobi and Gauss-Seidel, Jacobi tends to be less convergent than Gauss-Seidel. So Gauss-Seidel is always better. And that makes sense because you're always using a more updated information for Gauss-Seidel. Right? The only thing about Gauss-Seidel versus Jacobi is coding Gauss-Seidel might be a little more challenging than coding Jacobi, that's all. Alright? But still, Gauss-Seidel tends to be better. Now, there is a convergence criteria. Please note the criteria. The criteria says if the largest diagonal matrix, hold on, let me say it this way. If you're on a certain row or column, it doesn't matter. Everybody listening? If you're on a certain row or column, if the diagonal element, that's the one that's on the diagonal for that row, if the diagonal element is larger than all the sum of all the other elements in that row, that's it, the absolute value, or the modulus, or the magnitude of all the other elements in that row, then the criteria says Gauss-Seidel may converge. Alright? May converge. I'm sorry, it will converge. Beg your pardon. If it is not, then it still may converge. So what this is telling you is if you can confirm a situation in which you look on your diagonal elements, let me give you an example. For everybody, I want everybody to picture a 10 by 10 matrix. Okay, 10 by 10. Everybody draw your piece of paper. You have a 10 by 10 matrix. So you're going to have 10 diagonal elements. The one in the upper left hand is called A11. The one in the lower right hand is called A1010. And you're going to go to the third row. Everybody on the third row? I hope everybody is listening. Everybody on the third row? And on the third row, you're going to have the following elements. You'll have A. You should have A31, A32, A33, A34, and so on all the way to A310. That's just the third row. Everybody clear on that? What the Gauss-Seidel criteria says is if the magnitude of A33 is more than the sum of all the others' magnitudes, okay? If it's more than the sum of all the others' magnitudes, then your matrix will converge. Am I clear? Or then your Gauss-Seidel iteration procedure will converge. Alright? So you can appreciate Gauss-Seidel can be beneficial if you don't want to go through all the matrix inversion and all them something there. You can use Gauss-Seidel iteration to get to your answer if it is it may be appropriate to do that. Alright? Note therefore, if that is the case, then it clearly you should realize that if some matrices are what you call diagonally dominant, for example, remember I talked about the tridiagonal matrix some time ago, earlier this evening. Tridiagonal, that's an example of a diagonally dominant matrix. Okay? But diagonal dominant doesn't just mean the diagonal and the ones next to it. It just really means just the diagonal. Any matrix in which the diagonal is a very large number compared to the others, we call that a diagonally dominant matrix. Anytime you have a system with diagonally dominant system features, then Jacobi or Gauss-Seidel especially, Gauss-Seidel will converge, will likely converge. Okay? Remember, if it does not meet the criteria, you cannot say it will not converge. Okay? We're just not sure if it will. Alright? Alright, this other topic I'm not going to discuss. It is for you to do a little reading. It's a little challenging, but I don't want to get into it because some other topics we have to get into. That's eigensystems. Except to say, Paul, what you're saying? Unmute and say what you're saying, Paul. Oh, you're talking about.
You were saying that in some cases it may, based on the conditions that you observe, if it's diagonally dominant, then definitely you would say it would converge.
Right.
But if it does not hit that one, it may. That's what you're saying.
Yeah, it still may converge. Right. Good. Eigen problem. Sometimes you have a fourth unknown out of let's say three equations, four unknowns. Note what you see on your screen right now. Three equations, four unknowns. What are the three equations? You see them? And you have the four unknowns. The four unknowns are x1, x2, x3, and another term which is a coefficient of x1, x2, and x3. This is called an eigen problem. It is not quite a linear, it's not a completely linear system because the unknowns are not all linearly related. Okay, that eigenvalue, we call it here lambda, which is our fourth unknown, is in the system. But as you learn for criteria, remember, if the rank is less than the number of unknowns, you have multiple solutions. Remember that? Everybody clear on that? Rank. The rank is less than the number of unknowns, we have multiple solutions, right? That was for a plane linear system. Now this is not a plane linear system, this is called an eigenvalue, an eigenlinear system. But in this case, the rank is 3. That's three independent equations. But the number of unknowns is 4. So in this case, you also have what we call infinite number of solutions. The only thing with this system, however, is that the solutions are not, even though they are infinite solutions, they must have some relationship to each other. And those relationships, we call them eigenvectors. Alright? That's all I'll say for this. And I'm going to ask you guys to look through these slides. It's just 5 more slides to see if you can appreciate it. I think it's about 4 more slides. Alright? Alright. And and there's an example here at the end of the application of eigen problems. Alright, I may post a solution to this problem after you guys grapple with it a little bit. Alright, everybody, again, here's a repeat of the second assignment. It's due next week Sunday night. Please note, I actually said investigate. I said it in the so far in this session earlier. I said please investigate some of these functions. So you see LU. I did type LU last week when I was demonstrating the use of Octave. You see call, C-H-O-L, that's probably the Kolsky, right? But I need you to do a little investigation. In fact, when you do help, for example, type, if you open Octave or MATLAB and type help, H-E-L-P, space C-H-O-L, it's going to give you some help on that function call, to see what that function is. Everybody not sure what we're talking about here. Call. Hope everybody see what we're talking about. It's probably Kolsky decomposition, right? So it will tell you, give you information on call. At the end of every help, please note this, at the end of every help, or most helps in Octave or MATLAB, you will see a list of other related functions. Alright, so when you go to the bottom, you'll see some other possible decomposition functions. I want you to just have a look at them and have some discussion on them. I'm begging you guys to, I want to see you take some initiative and have some discussion amongst yourselves on the website. There is a forum. I know that WhatsApp is a nice place to just chit chat, but WhatsApp cannot keep threads. Everybody know what a thread is? Hello? Everybody know what a thread is? Hello? Right. Good. So let's say you're going to discuss a certain topic. You just start it in online in the discussion forum, and you can respond to any topic at any time. Alright, everybody gets the same posting. It goes to everybody's email. Everybody's clear on it. Alright, that's what I'm asking of you. Okay, here are some examples of common places where you have linear systems. In mechanics, force in a truss system, you have several forces, right? And each will have its own relationship. Different when you write out the expression, remember it's just mechanical equilibrium expressions that you write, and so you'll have a set of every point you write an equilibrium expression, right? For example, this point will have its own 2 based on forces in the x and the forces in the y. Another equation, another equation, another equation. So you'd have 1, 2, 3, 4, 5, 6 equations here. Good. And you have how many unknowns? 1, 2, 3, 4. Oh, hold on. Let's go that again. 1, 2, 3, 4. Let me mix up. Alright, this triangle is 3 right here. 3 points. And then you have 2 more points. And then 1 point. Yeah, that's 6. How many sides do you have? That would be the number of forces that you have to calculate now, right? We have 1, 2, 3, 4, 5, 6. Interesting. I see 8 here. I see 9 actually. But anyway, it will work. We're just not clear. Oh, no. Now I see what the issue is. What's the issue? Each one is 2 equations, right? Remember, it's a x and a y. X and a y. So it's actually 12 equations. How many and how many unknowns? Each leg is an unknown. So you have 3 here, 3 here, and 3 here. That's 3 unknowns. So 9 unknowns, because there are 9 members. So you have 12 joints and 9 members. So what does that mean? That means that of the 12, it's likely that 3 are dependent. So they can be reduced to 9 equations. Alright? So that's an example in mechanics. In electrical, here's another example. Suppose you want to know what's the current going through the system. If it's just a couple, it's kind of easy, but if it's a very complex circuit, then it becomes a little bit more complicated, right? In chemical or systems, here we have a set of CSTRs or CSTR, constant stirred reactor, or well stirred reactors, and fluid is going between them. Mixtures are going between them, and you want to know what is the concentration in each, right? Concentration here, which is the same as concentration 1, concentration 2, concentration 3, right? Clear? That would be 3 equations. Okay? 3 unknowns. Alright. Now the next topic is iteration. It's not really a next topic because I've already started iteration. I'm going to spend a little more than half hour on that, and I will call it quits for the day. Alright? Please everybody confirm when it loads. As soon as it loads, I want everybody to confirm that they're seeing the next PowerPoint. Alright. Would everybody kinda agree that there's one little hitch? I have to get my little tablet pen. That would make things a lot easier, which I could like mark on the slides and so forth. But generally everybody agrees that the online can sort of work. I wouldn't make it the main way, but you know, I still probably have some main lectures, but people who are not present, they can log in remotely, right? Yeah, when I get the pen, I think it will help.
Sir, will we see this recording on the website?
Yeah, man. If you look on the website, you'll see 2 recordings there already, right? Richard?
No, making reference to this particular one.
This one is being recorded as we speak.
Okay.
It will take a little time. So usually it's not posted immediately because it's recorded in some proprietary video format, and then I have to do some changing of the format to something that can go onto YouTube. We have a YouTube channel, a UTech Engine YouTube channel that I post these lectures on. So first I have to reduce it to a format for YouTube, and then I upload it to YouTube, and then I link it to the website. takes a little, not, it doesn't really take long, but you know, I'm a business sometime when I get, but I can't do it immediately, that's the point. Alright. So yeah, once I get the pen, I have my stylus, you know, but for some reason my pen can't find the pen for it somewhere here at home. Okay, so everybody should be seeing Unit 3, root finding. Okay, first point to note, everybody must be clear on this. When we speak of root finding, we are not talking about, we actually don't, oh boy, how should I say this? Tell you what, let me start the presentation and then I'll get to that point. Alright, root finding. And what you'll see here is iteration. This is really what I want to be clear on. This is really iteration, not so much root finding. The basis of this topic is that sometimes you don't have a linear system and you still need to solve your linear systems. Alright? Usually, however, we're going to start with the simplest type of problem you need to solve, which is one equation. Most times, it's pretty easy to solve one equation. You just kind of do some algebra, and eventually you isolate the term you're trying to solve for, and you're left with the rest of it, right? That's simple enough. But sometimes you can have a problem that you cannot solve algebraically for the unknown term. So that's what we are calling a root finding problem. Okay? Note, root finding is not the same as iteration. They're somewhat different. And we're going to look at the distinct difference between root finding and iteration. Note, root finding is a subset of iteration. Okay? It's a subset of iteration. There's another type of it, but it's the main one. There's another type of iteration called fixed point iteration, abbreviated FPI, fixed point iteration. Alright, we'll discuss them both. You just did Jacobi and Gauss-Seidel. Jacobi and Gauss-Seidel are examples of fixed point iteration. Alright? Everybody listening? So let me see if you're listening. What is the overall, what is the broader type of solution for nonlinear systems called? Good, iteration, correct. What are the two subsets of iteration? Root finding and it's not on the slide, the second one. I'm so used to typing, remember, look at this unmute and say it is alright.
Jacobi.
Okay, Jacobi and Gauss-Seidel are types of that second type. So root finding is one subset. Jacobi and Gauss-Seidel are examples of the other subset. The other subset is called fixed point iteration. Alright? And both Jacobi and Gauss-Seidel are examples of that. Albeit they are linear systems, but it's still applying the same iteration approaches. Alright? So note, to go through a few iterative methods. First one is called bisection, next one is called false position, next one is called fixed point iteration. You realize fixed point is called a type of iteration. Okay? The other 5 here are sorry, the other 5 here are actually by root finding methods, and fixed point iteration is all by itself, its own. Alright, so the 5, that's bisection, false position, Newton-Raphson, secant, and Mueller. Those are all root finding methods. Okay, let's talk about bisection first of all. Alright, everybody, I'm going to ask you to do something. I'll ask you to go to this website, open another Chrome tab or Firefox or whatever you're using, Edge, whatever tab whatever you're using. Open another tab. You're going to type in that URL for me. Also, I here have the 6th edition, but you need to be referenced to the 7th edition, and you need to know the 6th edition where to find this topic. Everybody gone to the website yet?
Yes, I'm there.
Okay. Alright. I just want you to be there. I will actually tell you to go there when to click on different things when I'm ready. Alright. Alright, so for the 6th edition of numerical methods, which I reference on the website, the 7th edition is the one that is the required text. Remember, I gave you a reference for 6th edition. It's on the website. The chapters covering iteration is in what's called part 2, that starts at page 113, or part 2 is chapters 5, 6, and 7. Okay, same chapters as 6 and 7. Alright, so I encourage you to read through these chapters over the next week. After I do the lecture during the week, you can do some reading in this chapter. Alright? Okay. Now, you're going to get another assignment coming up in us now. You better get yourself used to these assignments. I think I may go over this. Richard, I can mute you. Yeah, I think I'm going to probably do quite a bit of this topic next week, also. Not next week, week after next week also. So yeah, I think I will. Alright. So everybody I hope everybody has a copy of the 6th edition for your own reading. Please do. Please read. Okay? Don't leave it all on me to put it in your head. Now, let's keep going. What is iteration? Iteration is the definition of iteration. Common definition. This is definition in the regular world. Action or process of repeating a procedure in which repeating in which the repeating of the procedure results in you arriving closer to your desired result. Okay? It's called iteration. It means do something over and over and over and over again until you get it. But usually it's not over again, like randomly. So you try it once and then you try it again a second time, and the second time is just as random as the first time. You can't do iteration like that. You'll never get to the answer. What iteration is implying is that you try to do something, you learn from the first experience. You try again. Based on what you've learned from the first experience, you try again. You try again. Based on what you've learned from the first and second experience. You try again. Based on what you've learned from the first, second, and third, and so on. Obviously, you should be getting closer to the answer, right? Remember, anybody wants to know nothing, you can just unmute and say it. Just like if you're in class. Let's talk. Yeah? Yes, Paul. Fine tuning the previous one. Remember to talk if you want, though. Because every time I look down and read, you must remember that. You can't ignore if me hear somebody talk, but you might not really see if you type. Hope everybody understands that, sir. Alright? That's why I set up. I could have set up the Skype to be. Oh, your voice gone. Alright. Yeah. I could have set up the Skype to prevent everybody else from talking. But I set it up so that you all have equal contribution to the meeting as I do. The only difference is I'm the only one who is using the software called Skype Business. And I'm only doing that, and I require you all to use web, because when you use a web version, it actually makes the bandwidth more, it allows better streaming. Okay, because I'm making the presentation, I use the full software. Alright. Oh, Sean is using Skype, so that's fine. Hmm? Hey man, I'm in a class. We can come. Wow. I'm just mute it. I'm just mute it. They would have heard it. Wow.
You know how I was going to check on you?
Oh, no, that was it.
No, she was doing some.
Hmm?
She was doing some.
Okay. What you doing? What you doing?
I think she tagged me.
You got it, man.
With towns or to use this.
Hmm?
The towns or to use this.
I think it's smallpox killed them, not chicken pox.
What's the difference?
It's a different disease, man. That one that we kill. Close the door. Like how them come down and make noise, close the door for me so I can unlock it. The two of them. Sorry, my son came by, so I'm muted. I had to say a few things to him. So that's why you weren't hearing anything. Alright. Alright, so everybody clear what iteration is commonly, right? Now, in engineering, it is the process of initially guessing a solution for a problem and correcting or improving the solution from the initial guess to progressively more informed or better approximations by interpreting the results of the previous approximation. Okay? It's kind of obvious. Everybody understand? That's what iteration is. You iterate until you get close enough to the answer. Usually, you'll never get to the answer. You get close to the answer. How close you get is based on what you call your error criteria or your convergence criteria. Alright? Mute the dog Skype, sir. I don't understand what you're saying, Paul. Oh, yes, I must mute my dog. Put my dog outside. If you just bear with the dog, beg pardon. Anyway. And the dog was back in the background to me for mute. I'm amazed that Skype actually picked that up. Everybody can hear the dog about?
Can I hear the dog say?
Don't I hear mute because the dog says.
The dog about. But just imagine if you actually were here and I was doing the class at my house, you would hear the dog, right? And it wouldn't bother you. You don't make the dog bother you, man. Alright? Just like with the school and rain and fall and car drive outside, you don't hear it. Anyway. Alright, so you stop iterating when you're close enough to the answer. It's called the convergence criteria. Or sometimes it's called the error criteria. Okay? Okay, so what is the purpose of iteration from a math or engineering perspective? Note, if g of x is equal to h of x, all I'm saying is on the left hand side of the equation has a lot of terms. The only unknown is an unknown called x, and on the right hand side again the only unknown is a term called x. Let's see how I'm tired. Hear me, I yawn. Okay? The point is x is the only thing that you're solving for. Now, normally you would just do some algebra and you find x, but not everything can be solved algebraically. Whatever can't be solved algebraically, you use iteration to solve it. Okay? Here's an example. Beg pardon. It's an iterative procedure if you want to know. Sorry about that again. Wow. Sinuses are getting out of hand. I would might have to stop the class. Alright, let me try to bear through a little bit more. Just trying to set a foundation for iteration. Okay, again, iteration, two approaches. Look at the heading of this slide. Either root finding or fixed point. Alright, Yes, Sean, I shall avoid dairy and peanuts if I. Well, I can't avoid it. Why peanut too nice? No. Anyway, I have sinus. You know, everybody here have sinus. It's actually a gland in your in your head. It's called the sinus gland. Anyway, that's a deviation from the point. Back to the lecture. Everybody see the two types of iteration: root finding and fixed point. Alright? Root finding is where, remember the original problem we had? G of x equal h of x. Right? Root finding says put everything on one side and make it equal to 0. So it will be g of x minus h of x equal 0. That g of x minus h of x is what you could just call f of x. Okay? Just put everything together. Call it one thing. That's equal to 0. The root of an x equation, you should recall, means where is the function equals 0. That's what root means, right? For example, we talk about the roots of a polynomial. The question is, where is the polynomial equal to 0? I'm breaking up. Am I breaking up for everybody?
Brandon? Sorry, you're breaking up.
I don't know why I'm breaking up. Probably it's just a mess. It's just a sign for me to stop this class. Alright, here's what I'm going to do. Yeah, everybody says I'm breaking up. Not sure why. Let me check if my children are watching Netflix or something and I don't know about it. Give me a minute there. Let me say that again. Did everybody hear what I just said? I'm going to check if my children are watching Netflix or something like that. Did you hear me? Hello? I'm going to type a message. Alright, I'm back. Any better?
Much better.
Yes,
Alright.
clear.
Clear. Alright. Yeah. Two computers upstairs, one put it upon one, the next one up on the other, each one ready for what they want or something. So, alright. Alright, I'm going to wrap this up soon. I also want to go through the assignment. Everybody should have gotten a notification about the assignment. Did you? Everybody got the notification, right?
Sorry, look, I was feeling them gum up when I come to there.
No, I don't think so. Oh boy. Alright, good. I'm going to try and just bear through this presentation. Just a couple more minutes, alright? Let's just set the foundation. So you have root finding, which is in root finding you make everything equal 0, and fixed point finding you solve for one of the x's in your system. Remember, your system is just an equation that has x at different places. So for one of those x's, you're going to solve for that x. So that x is going to be some function of x. That means x equal to something something with x's in it. That's called a fixed point form of an expression. Or if you solve something and it is something 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 with x equals 0, that is called the root form of a expression. Okay, so you have the fixed point form and the root form. Fixed point just says what is the value for x that gives you about x, and the root form is what is the value for x that gives you 0. Okay, there are two general stages. Passing can't hear me. That means everybody can't hear me. Alright, let's call it quits for now. Okay, let's call it quits for now. Hold on. Alright. Everybody not hearing me, eh? Yeah, it is a sign. Yes, it is a sign.
I'm hearing you, but it's breaking up.
Yeah, understood. Alright, Devon. Still breaking up, not true. In and out. Alright. Not sure why.
Can you hear me now?
I'm hearing you guys quite well enough.
I have to go check upstairs again. Maybe actually come it up here.
Alright, let's work with it. May I wrap this up, alright? Let's deal with the I just saying there are two ways. There are two stages to start doing an iteration. The first general stage is to guess your solution. Still breaking up? Am I still breaking up? Hello? Still breaking up? Sometimes I just pause and pausing. Wow.
It's still breaking up.
Wow. Alright. That means that we must stop. Alright, so I'm going to stop. Everybody saw the project. It should be clear. If it is not clear, send me questions through WhatsApp or the website to clarify anything. If it is something that you need answers, structured answer, check. I'm typing. Note the due date. Any questions? Ask early. Yeah, WhatsApp or email the questions. I prefer website forum for questions. Let everyone see your questions. Right? Remember, so remember, Orlando needs group members, so consider shifting yourselves around. Extension already. Why you want extension for what? Oh, website just went down.